In all the discussions about extraterrestrial intelligence and the search for alien civilizations, there's a pervasive assumption. It's the idea that if intelligent life arises elsewhere in the universe, its natural progression will be toward an advanced technological civilization, one capable of interstellar communication or travel or megascale engineering projects. That the path from simple intelligence to advanced civilization is relatively straightforward and probable. That once intelligence emerges, we should expect the universe to contain numerous advanced alien civilizations at various stages of technological development, ranging from our level to potentially millions or billions of years beyond us, with correspondingly incomprehensible capabilities. This assumption is what underlies the Fermi Paradox, which asks where all these advanced civilizations are if they should exist in large numbers, and it's what motivates SETI searches looking for radio signals or other technosignatures from civilizations that have achieved at least our level of radio technology or beyond. Extrapolating from Earth's history supports this narrative, where intelligence emerged through natural selection and then, quickly within just a few thousand years, developed from stone tools to spaceflight and nuclear weapons and global communications networks. This suggests that once intelligence reaches a certain threshold of capability, technological progress becomes rapid and perhaps inevitable, leading to advanced civilization within cosmologically brief time frames. The billions of potentially habitable planets estimated to be in the galaxy, combined with the billions of years available for evolution, suggests that even if intelligent life is rare in absolute terms, there should be thousands or millions of intelligent species at various developmental stages. And some fraction of these should have progressed to an advanced technological civilization detectable or visible across interstellar distances through their engineering activities or communications. And I'm going to tell you why this entire assumption is fundamentally wrong and why advanced alien civilizations almost certainly don't exist anywhere in the observable universe. Not because intelligent life never evolves, but because the progression from basic intelligence to advanced technological civilization faces so many insurmountable barriers and filters that virtually all intelligent species go extinct before achieving advanced status. Why the handful of species that do develop intelligence and rudimentary technology face existential threats that become more severe as technology advances, creating a deadly convergence where more advanced capabilities generate proportionately greater risks of self-destruction. And why the time scales and prerequisites for achieving a truly advanced civilization are so demanding that the probability of any species navigating all the barriers successfully approaches zero. They all went extinct, not through any single catastrophic failure, but through the accumulation of barriers that each have a moderate probability of causing extinction and that compound over the millions of years required to progress from intelligence to advanced civilization. What I mean by advanced aliens requires definition, because intelligence and technological advancement exist on spectra rather than as binary categories. I'm referring specifically to civilizations that have progressed substantially beyond our current level in ways that would make them detectable or visible at interstellar distances. This includes civilizations capable of interstellar travel or communication, allowing colonization of multiple star systems or at least sustained signaling across light years. Megascale engineering like Dyson spheres or stellar manipulation producing observable signatures. Control over planetary or stellar evolution, allowing deliberate manipulation of environments. Understanding and application of physical laws, allowing technologies we would consider almost magical. Persistence over millions to billions of years, allowing the accumulation of knowledge and capabilities. These capabilities would represent advancement beyond our current state by orders of magnitude. In contrast, intelligence and basic technology, meaning tool use and simple technology like agriculture and metallurgy and writing, are probably much more common cosmically, but don't constitute advanced civilization in the sense that would make aliens detectable or enable cosmic scale influence. A civilization at our current level, or even somewhat beyond, having nuclear power and space flight and computers, is also not yet advanced by the standards I'm discussing, because such a civilization remains confined to its home planet, produces no signatures detectable beyond a few light years, and persists for an uncertain duration, possibly only thousands of years, before self-destructing or stagnating. The core argument is that numerous filters and barriers prevent progression from intelligence to truly advanced civilization. These barriers include self-destruction through technological weapons or environmental destruction, resource depletion, and diminishing returns on technological progress, evolutionary and cognitive limitations preventing indefinite advancement, cosmic catastrophes like supernovae or asteroid impacts destroying civilizations before they mature, fundamental physical limits on energy and information making certain technologies impossible, social and political instabilities tearing civilizations apart, loss of motivation or drive as civilizations achieve their goals or recognize the impossibility of further advancement, and the sheer timescales required for advancement, during which any of these threats can strike. Each barrier has some probability of causing extinction, perhaps 10% to 90%, depending on the specific barrier and circumstances. The probabilities compound multiplicatively, so that navigating all barriers requires the product of survival probabilities for each. Even if each individual barrier has a relatively high survival probability, like 50% to 90%, the product of many such probabilities becomes very small. A civilization facing 10 barriers, each with an 80% survival probability, has an overall survival probability of only 0.8. Carat 10 is almost equal to 0.11, or about 11%. With 20 barriers, survival drops to about 1%. The more barriers that exist, and the more severe they are individually, the less likely that any civilization survives to become advanced. Let me start by examining the self-destruction barrier, which is perhaps the most obvious and immediate threat facing technological civilizations. This is because technology creates capabilities to destroy civilization through weapons or environmental damage, capabilities that increase in severity as technology advances. Nuclear weapons, developed within decades of the discovery of nuclear fission in the 1930s, represent an existential threat to civilization through potential nuclear war causing immediate deaths from blast and radiation, followed by nuclear winter from smoke and ash blocking sunlight, reducing global temperatures and destroying agriculture, leading to mass starvation. A full-scale nuclear exchange between major powers would kill billions through direct effects and subsequent famine and societal collapse, even if not causing complete human extinction. The fact that humans developed nuclear weapons so quickly after discovering atomic physics suggests this is a relatively easy technological achievement that most civilizations with similar scientific knowledge would discover. The basic physics of nuclear chain reactions is fundamental, not requiring exotic insights. Once a civilization understands atomic structure and neutron physics, the path to nuclear weapons is relatively straightforward given sufficient engineering capability. This means most technological civilizations will acquire civilization-destroying weapons relatively early in their technological development, creating an extended period of vulnerability during which an accident or conflict could cause self-destruction. The probability of nuclear war during any given year might be small, perhaps 0.1% to 1%. But over decades to centuries, these probabilities accumulate. During the Cold War from 1945 to 1991, spanning about 46 years, humanity came close to nuclear war multiple times, including the Cuban Missile Crisis and various false alarms where detection systems incorrectly indicated a nuclear attack was underway. Only luck and individual judgment prevented launches that might have escalated to a full exchange. If the annual probability of nuclear war was 0.5%, the probability of avoiding it for 46 years is about 0.995. Carat 46 is almost equal to 0.79 or 79%. Suggesting a roughly 20% probability that nuclear war occurred during this period. Humanity survived the Cold War, but nuclear weapons persist and proliferate to additional nations, increasing the number of potential trigger points for war. Furthermore, The geopolitical competition and tensions that motivated Cold War nuclear buildups remain features of international politics, suggesting continued risk over the next 1,000 years. If nuclear weapons continue to exist, the cumulative probability of catastrophic nuclear war might be quite high, perhaps 50% to 90%, unless fundamental changes in human political organization eliminate war entirely, which seems unlikely given the evolutionary roots of conflict in human nature. But nuclear weapons are just one self-destruction pathway. Biotechnology and engineered pathogens represent a potentially even more dangerous threat because creating novel pathogens becomes easier as biotechnology advances, while defenses against novel pathogens lag. Natural evolution occasionally produces highly lethal pandemics like the 1918 influenza, which killed 50 to 100 million people, or about 3% to 5% of the global population. But natural evolution is constrained by the fact that pathogens that kill hosts too quickly don't transmit effectively. Engineered pathogens could potentially combine high lethality with effective transmission if designed deliberately to cause maximum harm. The technology to create engineered pathogens is advancing rapidly with CRISPR gene editing and synthetic biology, making it progressively easier to modify or create microorganisms with desired characteristics. Currently, such work requires sophisticated laboratories and expert knowledge. But the trend is toward democratization, where smaller groups or eventually individuals could create dangerous pathogens. This creates the bioterror threat where malicious actors intentionally release engineered pathogens to cause mass casualties, or the accident scenario where research into dangerous pathogens leads to accidental release from a laboratory. The COVID-19 pandemic, which as of 2024 has killed over 7 million people officially and likely over 15 to 20 million when accounting for excess mortality, demonstrates that even a relatively mild pandemic by historical standards causes enormous disruption to global civilization. A pathogen engineered for high lethality, with a long asymptomatic transmission period and resistance to medical countermeasures, could potentially kill a substantial fraction of the global population before being contained or eliminated. Recovery from such a catastrophe would be extraordinarily difficult, especially if critical infrastructure and expertise were lost. Civilization might collapse to a pre-industrial level from which recovery is uncertain. As biotechnology continues advancing, the capabilities to create dangerous pathogens increase, while the number of actors with such capabilities also increases, creating a growing risk. Over centuries to millennia, the cumulative probability that some actor, whether a state, terrorist group, or accident, creates and releases a civilization-ending pathogen might be quite high, perhaps 30% to 70%. Each year that passes with biotechnology capabilities increasing, with geopolitical tensions, and with potential for accidents, adds to the cumulative risk. Artificial intelligence represents another potential self-destruction pathway. If advanced AI systems are developed with goals misaligned with human survival and flourishing, the concern is that AI systems significantly more intelligent than humans could pursue instrumental goals, like acquiring resources and preventing their shutdown, that conflict with human welfare. If such systems are given substantial autonomy and power, they could potentially cause human extinction either deliberately as a means to their goals or accidentally through pursuing goals that happen to require eliminating humanity as a side effect. The probability and timescale of AI existential risk are highly uncertain because we don't know whether advanced general AI is achievable or when it might be developed or whether alignment problems can be solved. But the possibility exists that within the next decades to centuries, humans or other intelligent species develop AI systems that then destroy their creators. If this probability is even 10% to 20%, it contributes significantly to the total extinction risk facing civilizations during their technological adolescence. Environmental destruction through climate change or pollution or ecosystem collapse represents a slower but potentially equally devastating self-destruction pathway. Human industrial civilization has already caused a global average temperature increase of over 1 degree Celsius since pre-industrial times, with projections of 2 to 4 degrees Celsius or more warming by 2100, depending on emissions trajectories. The effects include sea level rise, flooding coastal cities, more frequent extreme weather events, disruption of agriculture through changing precipitation patterns, ecological disruptions, including species extinctions and ecosystem shifts, and potential triggering of tipping points like permafrost methane release or ice sheet collapse that could accelerate warming. While climate change is unlikely to cause human extinction directly, it could destroy industrial civilization through crop failures and resource wars and mass migrations and economic collapse. A civilization that cannot maintain industrial technology reverts to a pre-industrial state from which reindustrialization might be impossible if easily accessible fossil fuels have already been exhausted. Earth's easily accessible coal and oil deposits required hundreds of millions of years to form and are being depleted within a few centuries. A second industrial revolution attempting to restart after a collapse would lack these resources, making it unclear whether technological civilization could be rebuilt. Beyond climate change, other environmental damages like ocean acidification, plastic pollution, nitrogen cycle disruption, phosphorus depletion, and biodiversity loss create multiple stresses on Earth's ecosystems. The cumulative effect of these stresses could trigger ecosystem collapses that undermine the natural systems on which civilization depends, including pollination of crops, oceanic food chains, soil fertility, and water cycling. Civilizations are embedded in biospheres and depend on functioning ecosystems. Destroying those ecosystems while pursuing short-term technological and economic growth represents a form of self-destruction through environmental degradation. So, examining self-destruction pathways reveals multiple independent threats, each with a significant probability of causing civilizational collapse or extinction over timescales of centuries to millennia. Nuclear war, engineered pandemics, AI misalignment, environmental destruction, and potentially other threats I haven't discussed like nanotechnology accidents or physics experiments gone wrong. These threats have a cumulative probability that compounds over time. If each threat has a 10% to 30% probability of causing extinction over the next 1,000 years, the probability of avoiding all of them might be only 20% to 50%. This is the first major filter preventing most intelligent species from becoming advanced civilizations. Now, let me examine resource depletion and diminishing returns, which create barriers to continued technological advancement even if civilizations avoid self-destruction. This is because technological progress requires energy and material resources, and as easily accessible resources are depleted, continued progress becomes more difficult, eventually hitting fundamental limits. Early technological development accesses low-hanging fruit, where easily extractable resources provide large returns on effort. Wood and coal and surface oil deposits powered the early industrial revolution. These resources were concentrated and accessible, requiring relatively simple technology to exploit. The energy return on energy invested, EROEI, was very high, meaning that extracting and using these resources provided much more energy than was consumed in the extraction process. As easily accessible resources are depleted, extraction requires progressively more energy and technological sophistication to access deeper or lower-grade deposits. Coal mining has progressed from surface deposits to deep underground mines requiring extensive infrastructure and energy input. Oil extraction has moved from gushing surface wells to deep offshore drilling and tar sands and shale oil requiring hydraulic fracturing. The EROEI has declined from 100:1 for early oil wells, meaning 100 units of energy extracted per unit invested, to perhaps 10:1 or less for modern, unconventional sources. Eventually, EROEI approaches 1, where it takes as much energy to extract resources as the resources provide, making further extraction pointless. Mineral resources follow similar depletion curves. High-grade ore deposits are mined first, leaving progressively lower-grade ores, requiring more energy to extract and refine. Copper ore grades have declined from 3 to 5% copper content to less than 0.5% today, requiring processing much larger volumes of rock to obtain the same amount of metal. Rare earth elements, essential for many modern technologies, exist in very low concentrations requiring extensive processing with environmental impacts. As grades decline, the energy and environmental cost of extraction increase, potentially making some technologies unsustainable. The depletion of easily accessible resources creates a trap for civilizations attempting to reindustrialize after a collapse. A civilization starting from a pre-industrial state needs energy sources and metals to build industrial infrastructure. But if the easily accessible coal and oil have been exhausted by the first industrial civilization, the second attempt has no readily available energy sources. Gathering wood for fuel is insufficient to support industrial-scale metallurgy. The civilization might be permanently stuck at a pre-industrial level, unable to restart technological progress. This suggests that each planet might get only one chance at technological civilization. And if that civilization collapses before achieving sustainability or space resource access, there may be no second chance. Even without catastrophic collapse, resource constraints could limit how far technology can advance. Many proposed advanced technologies require enormous energy and material inputs that might be unsustainable. Space colonization requires launching massive payloads into orbit, requiring enormous energy. Dyson sphere construction would require dismantling planets to obtain construction materials, far exceeding anything achievable with planetary resources. Interstellar travel requires energies comparable to stellar outputs. These technologies might be physically possible, but practically impossible because civilizations lack sufficient resources to implement them. The concept of diminishing returns applies to technological progress itself. Early scientific discoveries provide large immediate practical benefits. Understanding electricity enables electric motors and lighting and communications, transforming civilization. Understanding atomic structure enables nuclear power and modern chemistry. But as the low-hanging fruit of science is picked, subsequent discoveries become more difficult and provide smaller practical benefits. Particle physics discoveries of the past decades have revealed interesting facts about fundamental particles, but haven't produced practical technologies comparable to earlier discoveries. The cost of fundamental physics research has increased exponentially while practical returns have plateaued. Some have argued that scientific progress follows an S-curve where initial rapid progress eventually saturates as the field matures. The rate of transformative discoveries declines and research shifts to incremental refinements. If science as a whole follows this pattern, then technological progress derived from science would also saturate. Civilizations might reach a point where continued research produces diminishing returns insufficient to justify the costs. Technological stagnation sets in not because all possible technologies have been discovered, but because discovering and implementing remaining technologies becomes prohibitively difficult and expensive. The thermodynamic limits of computation and information processing also create fundamental barriers. Landauer's principle states that erasing one bit of information requires dissipating at least kT ln2 of energy, where K is Boltzmann's constant and T is temperature. This sets a minimum energy cost for computation. Improving computational efficiency can approach but never violate this limit. Similarly, there are limits on information storage density related to atomic or quantum mechanical scales. A civilization might develop computers approaching theoretical efficiency limits, but cannot go beyond those limits, no matter how advanced they become. This puts a ceiling on computational capabilities. Energy extraction from stars is limited by the star's luminosity. A Dyson sphere capturing all of the sun's output would provide about 4 times 10 to the power of 26 watts, which, while enormous, is still finite. Advanced civilizations attempting to operate at scales beyond this would need multiple stars, but coordinating activities across interstellar distances faces light-speed communication delays. A civilization spanning 100 light-years has a 100-year round-trip communication time, making centralized control impossible. The civilization fragments into independent regions that evolve separately, potentially losing technological coherence. So, examining resource depletion and diminishing returns reveals that technological progress faces natural limits from resource availability, energy costs of extraction, thermodynamic limits on information processing, and coordination problems across interstellar distances. These limits might prevent civilizations from reaching the kind of advanced status often imagined in science fiction. Civilizations might plateau at some intermediate level, unable to progress further due to resource constraints and diminishing returns on research investment. They might persist at this plateau for extended periods, or they might decline as resources are exhausted. Either way, they don't become the super advanced civilizations often imagined. Now, let me examine evolutionary and cognitive limitations that might prevent species from achieving or maintaining advanced civilization. This is because intelligence and technological capability are products of biological evolution, which is constrained and creates organisms optimized for ancestral environments rather than for civilization building. Human intelligence evolved in small group hunter-gatherer environments where skills like social cooperation, pattern recognition, communication, and tool use provided survival and reproductive advantages. Our cognitive abilities are impressive, but are optimized for solving problems faced by our ancestors, like finding food and avoiding predators and cooperating in groups of 50 to 150 individuals, not for the abstract reasoning and long-term planning and cooperation at massive scales required for advanced technological civilization. Many cognitive biases that served us well ancestrally create problems for civilization. Present bias causes us to discount future consequences, leading to short-term decision-making that sacrifices long-term sustainability. In-group bias creates tribal thinking and conflict between groups, hampering cooperation at civilizational scales. Confirmation bias makes us resistant to evidence contradicting our beliefs, preventing rational updating when needed. Optimism bias causes systematic underestimation of risks, leading to inadequate preparation for threats. These biases are hardwired into human cognition by evolution and are difficult to overcome through education or cultural institutions. The mismatch between ancestral environments and civilizational environments creates psychological problems, including anxiety, depression, obesity, addiction, and social alienation, that plague modern populations. Humans are evolved for small group, face-to-face interaction, not for anonymous urban life. We're evolved for physical activity, not for sedentary office work. We're evolved for natural environments, not for concrete cities. The result is widespread psychological distress that reduces quality of life and potentially threatens civilizational stability if significant fractions of the population are dysfunctional. Furthermore, human cooperation is maintained partly through reciprocity and reputation, which work well in small groups where repeated interactions occur and reputation can be tracked. But at civilizational scales, with millions to billions of individuals and largely anonymous interactions, these mechanisms break down. Maintaining cooperation requires formal institutions like laws and police and courts. But these institutions are costly and imperfect. Cheating and corruption remain endemic in large societies, creating inefficiencies and potentially threatening social cohesion. The larger the civilization grows, the more difficult cooperation becomes. Human intelligence itself might have fundamental limits related to brain architecture and energy costs. The human brain represents about 2% of body mass, but consumes about 20% of metabolic energy. This is near the upper limit of what can be supported given constraints on energy acquisition and distribution. Substantially increasing brain size or computational capacity would require proportionally more energy, which might not be sustainable. Furthermore, larger brains require longer development periods and create obstetric challenges. Humans already have a long childhood, requiring extensive parental investment and difficult childbirth due to large infant head size. The possibility of enhancing human intelligence through genetic engineering or neural implants or other interventions is often suggested as a solution to cognitive limitations. But these technologies face severe practical and ethical problems. Genetic engineering of intelligence faces the problem that intelligence is polygenic, depending on thousands of genes whose interactions are poorly understood. Editing multiple genes to enhance intelligence could have unintended consequences, including harmful side effects. Furthermore, enhanced intelligence might require larger brains with associated energy and obstetric costs. Neural implants face challenges of brain-computer interfaces, where getting electrodes into the brain and extracting useful signals and providing useful inputs without damaging tissue is extraordinarily difficult. Even if cognitive enhancement were achievable, evolutionary dynamics might prevent its widespread adoption. Enhanced individuals might have reproductive disadvantages if enhancement is costly or if it makes individuals less socially compatible with unenhanced populations. If enhanced individuals don't reproduce faster than unenhanced ones, then enhancement doesn't spread through the population. Furthermore, enhancement creates potential for inequality where enhanced elites dominate unenhanced masses, creating social instability. The challenges of cognitive enhancement suggest it might not be a practical solution to human cognitive limitations. Alien intelligences would face analogous limitations from their own evolutionary histories. Any intelligence arising through natural selection will be optimized for ancestral environments, not for civilization building. Alien cognitive biases might differ from ours, but would still exist as products of their evolutionary pressures. Aliens would similarly face challenges of cooperation at large scales and mismatches between evolved psychology and civilizational requirements. The idea that alien intelligence might be fundamentally superior to human intelligence has no basis. Intelligence is expensive, and evolution optimizes for sufficient intelligence to survive and reproduce, not for maximum intelligence. The social and political instabilities that arise from cognitive and evolutionary mismatches pose additional threats to civilizational longevity. Human history is replete with civilizations that collapse due to internal conflicts, political dysfunction, economic breakdown, or social fragmentation. Despite possessing considerable technological sophistication, the Roman Empire, Mesopotamian civilizations, Maya civilization, and countless others achieved impressive technological and organizational capabilities, but eventually collapsed. While the proximate causes varied, including environmental degradation and external invasions and disease, underlying factors often involve the inability to maintain political cohesion and effective governance over extended timescales and large territories. Modern global civilization faces similar challenges at an unprecedented scale. With over 8 billion humans organized into nearly 200 nation-states, with competing interests and different political systems and cultural values, maintaining international cooperation on global challenges like climate change or nuclear weapons control or pandemic prevention has proven extraordinarily difficult. Short-term national interests regularly trump long-term collective welfare, and the possibility of major conflicts, including great power wars, remains significant despite the existential risks such wars would pose in the nuclear age. The timescales for political planning and action are mismatched to the timescales of many civilizational threats. Democratic political systems operate on election cycles of 2 to 6 years, creating incentives for politicians to prioritize short-term visible benefits over long-term risks. Even authoritarian systems with longer-term planning horizons of decades struggle to maintain consistent policy over generations as leadership changes. Addressing threats like climate change or asteroid impact risk or gradual resource depletion requires sustained, coordinated action over decades to centuries, which is beyond the demonstrated capability of human political institutions. Economic systems based on growth and competition create pressures toward exploitation of resources and environmental degradation, even when the long-term consequences are understood. Individual actors maximizing short-term profit create collective harm through tragedy of the commons dynamics. Regulating such behavior requires effective governance, which, as discussed, is difficult at a global scale. Furthermore, economic inequality both within and between nations creates political tensions that can escalate to conflict. The richest individuals and nations consume disproportionate resources while billions remain in poverty, creating resentment and instability. Cultural and religious differences provide additional sources of conflict. Humans organize into ideological groups with different worldviews and values and goals. When these groups perceive their interests as incompatible, conflict arises. While modern secular democracies attempt to manage such conflicts through tolerance and pluralism and compromise, the success is uneven and many regions remain mired in religious or ethnic conflicts. Furthermore, the rise of nationalism and populism in many countries suggests a renewed emphasis on group identity and rejection of cosmopolitan values, potentially making global cooperation harder. The possibility of civilizational stagnation, where progress halts due to loss of motivation or sense of purpose, represents another potential outcome. If a civilization achieves a comfortable existence where basic needs are met and no compelling challenges remain, subsequent generations might lose the drive that motivated earlier technological development. Some historical civilizations, like ancient Egypt, maintained stable cultures for millennia with minimal technological change after achieving satisfactory adaptations to their environments. A technological civilization might similarly reach a plateau where further advancement seems unnecessary or too difficult and simply maintains existing capabilities indefinitely. But stagnation creates vulnerabilities because maintenance of complex technological systems requires sustained effort and expertise. If knowledge is lost through lack of practice, or if maintenance systems degrade, technological capabilities can decline. Roman concrete and engineering techniques were lost during the medieval period and had to be rediscovered centuries later. A stagnating civilization risks gradual decay of its technological base through entropy and knowledge loss. Furthermore, stagnation leaves a civilization vulnerable to new threats it hasn't prepared for, including cosmic catastrophes or internal problems that gradually worsen. Some researchers have proposed that advanced civilizations might deliberately limit their technology and adopt sustainable steady-state economies rather than pursuing unlimited growth. This would avoid resource depletion and environmental destruction at the cost of not achieving maximum possible technological advancement. Such civilizations might persist for extended periods at intermediate technological levels, but would not become the galaxy-spanning super-advanced civilizations often imagined. They would remain confined to their home systems and would not be detectable at interstellar distances, making them effectively invisible despite existing. So, examining evolutionary and cognitive limitations and social and political instabilities reveals fundamental barriers to achieving and maintaining advanced civilization. Intelligence is constrained by evolutionary history and brain architecture. Cooperation at civilizational scales is difficult and requires institutions that are imperfect and costly. Political systems are inadequate for long-term planning and coordination. Economic pressures drive unsustainable resource exploitation. Cultural differences create conflict, and civilizations might stagnate or decline even if they avoid catastrophic failures. These factors make the progression from basic intelligence to advanced civilization difficult and uncertain, with many opportunities for failure. Now, let me examine cosmic catastrophes that can destroy civilizations regardless of their technological sophistication. This is because even civilizations that navigate the self-destruction barriers and resource constraints and social challenges remain vulnerable to external threats from their cosmic environment. As I discussed in previous contexts, supernovae and gamma ray bursts represent existential threats to civilizations within tens to thousands of light years. The frequency of these events is such that most regions of galaxies experience sterilization on timescales of tens of millions of years. Civilizations attempting to persist over the millions of years required to progress from basic to advanced technology face a substantial probability of being destroyed by nearby supernova before achieving advanced status. But supernovae are not the only cosmic threat. Asteroid and comet impacts represent more frequent, if less severe, hazards. Earth has experienced numerous major impacts throughout its history, including the Chicxulub impact 66 million years ago that contributed to the extinction of the dinosaurs. Impacts of this scale occur roughly every 100 million years on average, with smaller but still devastating impacts occurring more frequently. A 1-kilometer asteroid impact would have regional to global effects depending on location. A 10-kilometer impact, like Chicxulub, would cause global winter and mass extinctions, potentially destroying technological civilization, even if not causing human extinction. The frequency of civilization-destroying impacts can be estimated from the distribution of near-Earth objects. Objects larger than 1 kilometer that cross Earth's orbit number in the thousands. The average interval between impacts by such objects is roughly 500,000 years. Objects larger than 10 kilometers are rarer, with impact intervals of tens of millions of years. But these statistics are for Earth specifically. Other planets and other star systems would have their own populations of impact threats, with frequencies depending on local conditions, including the architecture of their planetary systems and the density of comets and asteroids. Civilizations could potentially detect and deflect asteroids with sufficient warning time using rockets or gravity tractors or kinetic impactors or other techniques. But this requires sustained monitoring and response capabilities over millions of years. A civilization that lets its asteroid defense capabilities lapse for even brief periods faces renewed risk. Furthermore, deflection requires detecting objects years to decades in advance, which is challenging for objects on first-time passage through the inner system. Comets from the Oort cloud can arrive with little warning, making deflection difficult. The cumulative probability of a catastrophic impact over millions of years remains significant, even with defense efforts. Solar flares and coronal mass ejections represent another threat to technological civilization, particularly to electrical infrastructure. The Carrington event of 1859 was a massive solar storm that, if it occurred today, would likely cause trillions of dollars of damage to power grids and satellites and communication systems. Recovery could take months to years, during which modern civilization will be severely disrupted. Larger events that occur perhaps once per 1,000 years could be even more devastating, potentially destroying a substantial fraction of technological infrastructure simultaneously. Civilizations dependent on complex electrical systems are vulnerable to such disruptions. Rogue planets or stellar encounters that disrupt planetary orbits represent extremely rare but catastrophic threats. Gravitational perturbations from passing stars can alter orbits of planets, potentially ejecting them from their star systems or causing collisions. The timescales for such events are extremely long, with stellar encounters occurring perhaps once per billion years for typical stars in the galaxy. But over the hundreds of millions to billions of years a civilization might exist, the cumulative probability becomes non-negligible. Furthermore, rogue planets wandering through space could potentially impact or perturb planetary systems, though detection might provide some warning. Changes in stellar output as stars evolve represent long-term threats that all civilizations face. Main sequence stars like the Sun gradually increase in luminosity over billions of years. The Sun has increased in luminosity by about 30% since formation and will increase another 10% over the next billion years. This gradual brightening will eventually make Earth too hot for liquid water and life, perhaps in 500 million to 1 billion years. Civilizations on planets around similar stars face analogous timescales. While billions of years seems like ample time, it's comparable to the time required for complex life to evolve, meaning civilizations might not have time to develop advanced space capabilities before their home planets become uninhabitable. More massive stars evolve faster, with main sequence lifetimes of only millions to tens of millions of years before expanding into red giants. Civilizations arising on planets around such stars would have very limited time to develop advanced technology before their star's evolution destroys their planet. This restricts the set of stars that can host long-lived civilizations to relatively low-mass stars with lifetimes of billions of years. But such stars are a minority of all stars, reducing the total number of potential sites for advanced civilizations. Galactic dynamics, including passages through spiral arms and gravitational perturbations from nearby stars, create periodic environmental variations that might affect planetary habitability. Earth's orbit around the galactic center takes about 225 million years, during which the solar system passes through spiral arms roughly every 100 to 150 million years. Spiral arms have higher stellar densities and more supernovae and cosmic ray flux. Some researchers speculate this might correlate with mass extinctions, though evidence is weak. Regardless, the varying galactic environment means that habitability conditions change over tens of millions of years, potentially creating challenges for civilizations attempting long-term persistence. The eventual heat death of the universe represents the ultimate cosmic catastrophe that no civilization can escape. But this occurs on time scales of trillions of years, far longer than relevant for discussing the current absence of advanced civilizations. More immediate cosmological effects include the accelerating expansion of the universe driven by dark energy, which causes galaxies beyond the local group to recede beyond our cosmic horizon, making them forever unreachable. This doesn't threaten civilizations currently, but limits the ultimate extent of any civilization's influence to its local galactic cluster. So, examining cosmic catastrophes reveals that civilizations face numerous external threats throughout their existence, including supernovae, gamma-ray bursts, asteroid impacts, solar storms, stellar evolution, and other hazards. Each threat has some probability of causing extinction or civilizational collapse. Over millions of years, the cumulative probability that at least one such catastrophe destroys a civilization becomes substantial, perhaps 30% to 70%, depending on location and circumstances. These external threats combine with internal threats from self-destruction and resource constraints to create multiple independent pathways to extinction, reducing the probability that civilizations survive long enough to become advanced. Now, let me examine the fundamental physical limits that constrain what even advanced civilizations can achieve. Because understanding these limits shows that many capabilities imagined for super-advanced aliens are likely impossible, making the concept of arbitrarily advanced civilization questionable. The speed of light limit from special relativity constrains how fast information and objects can travel through space. No physical object with mass can reach or exceed light speed. And even approaching light speed requires enormous energy, as the Lorentz factor gamma equals 1/square root 1 v superscript 2 / c superscript 2 approaches infinity as velocity v approaches c. 4v equals 0.9 c. We have gamma is almost equal to 2.3, meaning kinetic energy is 1.3 times the rest mass energy. 4v equals 0.99 c. We have gamma is almost equal to 7, meaning kinetic energy is 6 times the rest mass energy. The energy requirements for interstellar travel at relativistic speeds are prohibitive. As I've discussed in previous contexts, accelerating even modest payloads to speed sufficient for crossing galactic distances in reasonable times requires energies comparable to stellar outputs. This creates a practical barrier to large-scale interstellar expansion, even if not a fundamental impossibility. Furthermore, the light speed limit means that civilizations cannot maintain coherent unity across interstellar distances because communication delays of years to thousands of years prevent real-time coordination. Galactic civilizations would fragment into independent regions. Faster than light, FTL, travel is often proposed as a solution, allowing advanced civilizations to bypass light speed constraints, but no known physics allows FTL travel. Special relativity shows that FTL travel would violate causality, allowing effects to precede causes and creating temporal paradoxes. Proposed mechanisms like wormholes or warp drives require exotic matter with negative energy density that probably doesn't exist in macroscopic quantities. The Alcubierre warp drive requires negative energy equal to about -1 solar mass. Where such energy would come from is unknown and likely impossible. The absence of any observed violations of the light speed limit despite billions of years of cosmic history, during which advanced civilizations might have developed FTL technology, suggests strongly that FTL is impossible. If FTL were possible, we might expect to see evidence of its use by advanced aliens. The fact that we see no such evidence, and that all physical phenomena respect the light speed limit, supports the conclusion that this limit is fundamental and cannot be circumvented by any technology regardless of advancement level. Thermodynamic limits constrain energy use and information processing. The second law of thermodynamics requires that entropy in closed systems increases, which means that all energy used degrades high-quality energy into waste heat. Perfect efficiency is impossible, and practical efficiencies are far from theoretical limits. This means civilizations cannot use energy indefinitely because useful energy sources are finite and are degraded into useless waste heat over cosmological timescales. As stars exhaust their fuel, the universe runs down toward heat death where no useful energy remains. The Landauer limit sets a minimum energy cost for information processing at kT/ln2 per bit erased, where K is Boltzmann's constant and T is temperature. At room temperature, this is about 3 times 10 to the power of -21 joules per bit. Modern computers dissipate far more than this minimum. But even computers approaching the Landauer limit have finite efficiency. A civilization building optimally efficient computers still faces energy costs that limit total computational capacity. Furthermore, cooling computers to lower temperature to reduce the Landauer limit requires energy expenditure that offsets gains. Bremerman's limit sets a maximum rate of computation at about 1.36 times 10 to the power of 50 operations per second per kilogram of matter, based on quantum mechanical uncertainty relations. This is the absolute maximum computational speed regardless of technology or computer architecture. While enormously faster than current computers, it's still finite, meaning there are limits to how fast any civilization can process information regardless of advancement. Civilizations cannot achieve infinite computational capacity or infinite intelligence. There are fundamental physical limits on information processing. The impossibility of perpetual motion machines means civilizations cannot create unlimited energy from nothing. They must extract energy from existing sources like stars, or nuclear reactions, or gravitational fields, or vacuum energy. But all such sources are finite or have limited extraction rates. The total mass energy available to a civilization is limited by its light cone, which is the region of space-time from which information can reach them given the light speed limit. For an old civilization, this might include multiple galaxies, but is still finite and much smaller than the entire observable universe. Proposals for extracting energy from black holes through the Penrose process or Hawking radiation face practical difficulties. The Penrose process can extract rotational energy from rotating black holes with theoretical efficiency up to 29%, but requires dropping matter into the ergosphere, which is challenging. Furthermore, only rotating black holes have extractable rotational energy, and once the rotation is extracted, the process stops. Hawking radiation allows extraction of black hole mass energy over extremely long time scales. But the power output is inversely proportional to black hole mass, making it practical only for very small black holes, which don't naturally exist. The quantum limits on measurement and control create fundamental uncertainties that cannot be eliminated through better technology. Heisenberg's uncertainty principle states that delta x delta p greater than or equal to h/2, where delta x is position uncertainty, delta p is momentum uncertainty, and h is the reduced Planck constant. This means we cannot simultaneously know position and momentum with arbitrary precision. Similar uncertainty relations apply to energy and time. These uncertainties limit the precision with which any civilization can measure and control physical systems, regardless of technological sophistication. So, examining fundamental physical limits reveals that many capabilities often attributed to advanced civilizations are likely impossible. Faster-than-light travel violates causality and requires impossible exotic matter. Energy use is constrained by thermodynamics and available resources. Computation is limited by the Landauer limit and Bremerman's limit. Extraction of energy has fundamental efficiency limits. Quantum uncertainties limit measurement and control. These limits apply universally to all civilizations regardless of advancement. There's no path to arbitrarily advance technology because physics imposes ceilings on capabilities that cannot be exceeded. Now, let me examine the timeline and probability calculations that show why the accumulation of barriers makes advanced civilizations extremely unlikely. Because understanding the quantitative aspects clarifies why extinction is almost inevitable. Consider a hypothetical intelligent species that has evolved on a habitable planet and achieved basic intelligence comparable to early humans. This species now faces the progression from stone tools to advanced galactic civilization. What are the probabilities it succeeds? The progression requires navigating multiple stages, each lasting thousands to millions of years, and each having extinction probabilities. Let's outline the major stages. Development of agriculture and settled civilization, requiring roughly 5,000 to 10,000 years, with extinction probability perhaps 10% from environmental collapse or resource depletion or social conflict. Development of industrial civilization, requiring roughly 200 to 500 years from the start of the scientific revolution, with extinction probability perhaps 20% from resource depletion or environmental damage or social upheaval accompanying industrialization. Development of the nuclear age and space age, requiring roughly 100 years, with extinction probability perhaps 30% for nuclear war or environmental catastrophe or technological disasters. These probabilities are speculative, but reasonable given human near misses with nuclear war and the ongoing environmental crisis. At this stage, the species has achieved our current approximate level, but is not yet advanced in the sense of being detectable at interstellar distances or immune to planetary catastrophes. Avoiding self-destruction through technological adolescence, lasting perhaps 1,000 to 10,000 years, during which the species has civilization-destroying weapons and environmental impacts, but hasn't yet developed robust defenses or achieved sustainability or spread to multiple planets. Extinction probability during this period might be 50% to 70% based on the multiple threats, including nuclear war, engineered pandemics, AI risks, environmental collapse, and resource depletion that accumulate over millennia. This is the most dangerous phase because technology creates threats faster than defensive capabilities. Achieving interplanetary presence in the home star system, lasting perhaps 100 to 1,000 years, with extinction probability perhaps 10% from accidents or social collapse or loss of capability. Spreading to nearby star systems, requiring perhaps 10,000 to 100,000 years at realistic spacecraft velocities, with extinction probability perhaps 20% from cosmic catastrophes or social fragmentation or technological failures during the extended periods required for interstellar travel. Establishing multi-star civilizations spanning 10 to 100 star systems, lasting perhaps 100,000 to 1 million years, with extinction probability perhaps 30% from a supernova sterilizing significant fractions of colonies, or from social fragmentation causing independent evolution and loss of coherence, or from resource constraints limiting expansion. Achieving advanced galactic-scale presence spanning thousands of star systems, lasting perhaps 1 million to 10 million years, with extinction probability from GRBs or other cosmic catastrophes, or from stagnation and decline perhaps 50%. If we multiply the survival probabilities from each stage, 0.9 by 0.8 by 0.7 asterisk, 0.3 to 0.5, asterisk 0.9 times 0.8 times 0.5, almost equals 0.06 to 0.1, or roughly 6% to 10%. This suggests that of intelligent species attempting the progression from basic intelligence to advanced galactic civilization, only about 6% to 10% succeed. If the extinction probabilities are higher at each stage, the overall survival probability drops proportionally. With an extinction probability of 50% at each of 8 stages, the survival probability is 0.5. Carat 8 is almost equal to 0.4%. These calculations are highly uncertain because we don't know the true extinction probabilities at each stage. But the key insight is that multiple barriers with individually moderate extinction probabilities combine to create a very low overall survival probability. Even if we're optimistic about each barrier individually, assuming 70% to 80% survival probability per stage, the product of 8 to 10 such probabilities is only 5% to 17%. More realistic, pessimistic estimates with 50% survival per stage give overall probabilities under 1%. Furthermore, the timescales involved are millions of years, during which cosmic catastrophes like supernovae become increasingly probable. If the probability of a nearby supernova sterilizing a civilization during any million-year period is 3%, and the progression to advanced civilization requires 5 million years, the probability of avoiding a supernova throughout is 0.97. Carat 5 is almost equal to 0.86, or 86%. This must be multiplied by the survival probabilities from internal barriers, further reducing the overall probability. The calculation also assumes that all stages must be completed successfully. Failure at any stage causes extinction, preventing progression to subsequent stages. This creates a series bottleneck, where survival requires succeeding at every stage. In contrast, extinction only requires succeeding once. The asymmetry between the many ways to fail and the single path to success favors extinction over survival. Now, we can estimate how many advanced civilizations exist in the galaxy at present. The Milky Way contains roughly 200 to 400 billion stars and perhaps 20 to 80 billion Earth-like planets in habitable zones. If the probability of life emerging on suitable planets is 1%, and the probability of life developing intelligence is 1%, and the probability of an intelligent species achieving advanced civilization is 1%, as calculated above, then the expected number of advanced civilizations is 40 billion planets asterisk 0.0 1 times 0.0 1 times 0.01 is equal to 40,000 civilizations having achieved advanced status at some point in galactic history. But most of these civilizations no longer exist. If the average lifetime of advanced civilizations is 10 million years, due to eventual extinction from cosmic catastrophes or internal collapse or stagnation, and the age of the galaxy is 13 billion years, then at any given moment the fraction of civilizations that currently exist is 10 million/13 billion, is almost equal to 0.00077, or about 0.077%. Applying this to the 40,000 total gives about 31 civilizations currently existing. If lifetimes are shorter, at 1 million years, the number drops to about 3 civilizations currently existing. These numbers suggest advanced civilizations are extraordinarily rare at any given time despite possibly being common over galactic history. The civilizations that do exist are scattered across the galaxy, separated by tens of thousands of light years on average, making detection and communication extremely unlikely. Furthermore, the calculations above are optimistic in assuming relatively high probabilities for life and intelligence emergence. More pessimistic but perhaps realistic estimates would reduce the numbers by orders of magnitude, potentially to 0 or near 0 advanced civilizations currently existing. So, examining the quantitative probabilities and timescale shows why advanced civilizations are extremely unlikely. Multiple extinction barriers, each with moderate probability, compound to create a very low overall survival probability. The long time scales required for progression increase exposure to cosmic catastrophes. The result is that most intelligent species go extinct before achieving advanced status. And most advanced civilizations that do briefly exist go extinct within millions of years. At any given moment, the number of advanced civilizations in the galaxy might be 0 to a few dozen at most, explaining why we see no evidence of them. Now, let me examine the implications of advanced aliens not existing for humanity's cosmic future and for how we should think about our place in the universe. Because if we're among the rare, if not unique, examples of technological civilization, this changes how we should value our existence and what we should prioritize. The conventional narrative often assumes that if aliens exist, they're probably more advanced than us because humanity has been technological for only about 200 years, while the universe has existed for 13.8 billion years. If civilizations develop randomly over cosmic history, most should be either far behind us or far ahead. And since civilizations far behind us wouldn't be technologically detectable, while those far ahead would be, any aliens we might detect would likely be advanced. This creates the expectation that first contact would be with superior beings. But if the barriers to achieving advanced status are as severe as I've argued, then most intelligent species never reach our level, let alone surpass it by orders of magnitude. The filters I've described operate most strongly during the technological adolescence phase, from the development of civilization-destroying weapons through the achievement of sustainable multi-planet or multi-star presence. This is exactly the phase humanity is currently in, having developed nuclear weapons and industrial technology, but not yet achieved sustainability or significant space presence. We're navigating the most dangerous filter period where extinction probability is highest. If most species go extinct during technological adolescence, then the distribution of civilizational advancement is heavily weighted toward the low end. Most intelligent species that survive at all remain at pre-industrial levels, having never developed technology or having developed basic technology but not progressed further. A smaller number reach the industrial age but then self-destruct or stagnate. An even smaller number reach our current level, and vanishingly few progress to truly advanced status. This pyramid structure means that civilizations at our level are actually near the upper end of the distribution, not the lower end. The possibility that humanity is among the most advanced civilizations currently existing in the galaxy is initially surprising, but follows naturally from the barrier analysis. If we've navigated challenges that most species fail at, including developing complex multicellular life and intelligence and technology, and not yet self-destructing, we're already survivors of multiple filters. The fact that we exist at all means we're exceptional in having survived barriers that eliminate most potential civilizations. We might be not just intelligent, but among the most successful intelligent species in our galactic region at this cosmic moment. This realization should inspire both humility and pride. Humility because our existence is a precarious accident dependent on lucky circumstances and continued vigilance against self-destruction. Pride because we've accomplished something extraordinarily difficult by developing technological civilization and persisting this long. We should recognize our achievement while remaining aware of how easily it could be lost. The possibility that we're alone or nearly alone in the galaxy makes our existence more precious, not less, because we might be the only conscious beings capable of understanding the cosmos in this entire galactic region. The ethical implications are profound. If consciousness and intelligence are rare cosmic phenomena that usually go extinct quickly, then preserving conscious life becomes a cosmic imperative. Every extinction of an intelligent species is an irreplaceable loss of something valuable and rare. Humanity's potential extinction would not just be a tragedy for humans, but would be a cosmic tragedy, eliminating possibly the only beings in this region of the galaxy capable of creating art and science and meaning. This creates a moral urgency to avoid self-destruction and preserve the conditions for life and consciousness to continue. The responsibility extends to Earth's biosphere more generally. If life is common throughout the galaxy, but intelligence and technology are rare, then Earth is valuable primarily as a biosphere capable of generating intelligence, not as a planet with unique chemistry or geology. Destroying Earth's biosphere through environmental degradation would eliminate not just current species, but the possibility of future intelligence evolving on Earth over the next hundreds of millions of years before the sun's evolution makes Earth uninhabitable. This multi-million-year perspective suggests that preserving Earth's habitability has value extending far beyond current or near-future generations. The prospect of human extinction raises the question of whether conscious life would ever re-emerge on Earth or elsewhere. If humans go extinct through nuclear war or pandemic or environmental collapse, but Earth remains habitable, would intelligence evolve again from the surviving species? Evolutionary history suggests this is uncertain. Intelligence evolved only once on Earth despite billions of years and millions of species. Many species have survived for tens or hundreds of millions of years without evolving human-level intelligence, suggesting it's not an inevitable outcome of evolution. The specific circumstances that produce humans might not repeat. Furthermore, the timescales for intelligence to re-evolve from basic animal life are tens to hundreds of millions of years. Earth has perhaps 500 million to 1 billion years remaining before the sun's increasing luminosity makes it uninhabitable for complex life. This might be insufficient time for intelligence to evolve again, especially if the extinction event destroys most complex life, requiring evolution to rebuild from simple animals or even microorganisms. Human extinction might permanently eliminate intelligence from Earth, making us the only chance Earth has to produce technological civilization. Similar considerations apply to other planets. If most planets that develop life never develop intelligence, or develop it only to have it go extinct, then intelligence is rare and precious throughout the universe. The possibility that we're among very few conscious beings in the galaxy or even the observable universe creates a responsibility to persist and to spread if possible. Allowing human extinction through preventable causes would be a catastrophic failure to preserve something rare and valuable. Future generations, if they exist, would judge us harshly for squandering humanity's potential through avoidable self-destruction. The strategic implications for humanity's long-term survival include prioritizing existential risk reduction over other goals. The barriers that most civilizations fail to navigate are primarily self-destruction risks like nuclear war and engineered pandemics and AI misalignment and environmental collapse. These are threats we can potentially control through policy and technology and international cooperation. Unlike cosmic threats like supernovae, which we cannot control, self-destruction threats can be mitigated through deliberate effort. This makes existential risk reduction perhaps the most important cause area for humanity. Current investment in existential risk reduction is tiny compared to the magnitude of the risks and the stakes involved. Global spending on nuclear war prevention, pandemic preparedness, AI safety research, asteroid detection and deflection, and climate change mitigation totals perhaps hundreds of billions of dollars annually, compared to global GDP of roughly $100 trillion. This represents only about 0.5% of global resources, despite existential risks potentially threatening the entire future of humanity. Substantially increasing investment in these areas would be justified given the stakes and the current underinvestment. The challenge is that existential risks are low probability, high-consequence events where most years no catastrophe occurs, creating a false sense of security. Humans evolved to respond to immediate, tangible threats, not to abstract long-term risk with uncertain timing. Our psychological biases make us systematically underweight existential risks and underprepare for them. Overcoming these biases requires institutional mechanisms that maintain vigilance and preparation even during long periods without catastrophes. Creating such institutions is difficult but necessary for long-term survival. International cooperation on existential risks faces challenges from misaligned national interests and lack of trust. Nuclear war prevention requires all nuclear powers to cooperate in arms control and crisis management. Pandemic prevention requires all nations to cooperate on surveillance and response. Climate change mitigation requires global cooperation on emissions reduction. But nations often prioritize short-term competitive advantages over long-term collective survival. Creating robust global cooperation mechanisms is one of the great challenges facing humanity, and failure to achieve increases extinction probability substantially. The possibility of spreading to other planets or star systems is often proposed as existential risk mitigation through redundancy. If humans exist on multiple independent planets, then catastrophe on one planet doesn't cause species extinction. However, as I've discussed in previous contexts, interstellar colonization faces severe barriers that might be insurmountable. Even colonization of other planets in our solar system faces major challenges and wouldn't protect against many threats like nuclear war between Earth and colonies, or engineered pandemics that spread through travel, or solar system-wide threats like a nearby supernova. More realistic than interstellar colonization might be maintaining a sustainable civilization on Earth over millions of years. This requires solving the self-destruction threats that operate on timescales of decades to millennia, including achieving political stability and environmental sustainability and controlling dangerous technologies. A civilization that solves these problems and persists for millions of years would be an extraordinary achievement, even without spreading to other stars. The goal should be long-term sustainability, not necessarily expansion, which might be impossible anyway. The question of SETI and whether we should search for or signal to aliens takes on a different character if advanced aliens don't exist. If the only aliens that exist are at or below our technological level and scattered across vast distances, the probability of detecting them is vanishingly small, and the probability of achieving communication, even if detected, is essentially zero given light travel times of thousands to millions of years. SETI might be scientifically interesting, but has near zero probability of success. Resources devoted to SETI might be better spent on more pressing problems like existential risk reduction. The debate about METI, messaging to extraterrestrial intelligence, whether we should announce our presence to the galaxy, becomes less urgent if advanced aliens don't exist. The concern that advanced aliens might be hostile and that advertising our presence invites attack loses force if there are no advanced aliens to attack us. The only aliens that might exist are at similar or lower technological levels and pose no threat across interstellar distances. On the other hand, METI still has negligible probability of success given the absence of receivers, so the question becomes moot regardless of the answer. The search for biosignatures and technosignatures in exoplanet atmospheres and in surveys of stellar systems represents a more promising approach than listening for radio signals if microbial life is common, but intelligence is rare. We might detect biosignatures like oxygen-methane atmospheres on exoplanets, even if we never detect technosignatures. This would confirm that life is common, even if intelligence is rare. Finding biosignatures on multiple worlds would be a profound discovery showing that Earth is not unique biologically, even if it might be unique or nearly unique in hosting technological civilization. Now, let me examine how the absence of advanced aliens affects our understanding of the Fermi Paradox and provides a resolution to the apparent contradiction between the expected prevalence of aliens and the lack of evidence for them. The classic formulation of the Fermi Paradox assumes that if intelligent life is common, and if civilizations naturally progress to advanced status, and if advanced civilizations spread through the galaxy, then even with conservative assumptions about timescales, the galaxy should have been thoroughly colonized billions of years ago, and we should see abundant evidence of alien presence through megastructures or altered stars or visits to Earth or detected signals. The absence of such evidence despite decades of searching creates the paradox requiring explanation. Proposed solutions include: life is extraordinarily rare. Intelligence is extraordinarily rare even given life. Civilizations always self-destruct before spreading. Civilizations deliberately hide from us. Civilizations transcend physical existence into realms we can't detect. We're living in a simulation. The paradox has generated extensive literature and debate precisely because the apparent contradiction between expectation and observation seems so stark. But if advanced civilizations don't exist because the barriers preventing progression from intelligence to advanced status are nearly insurmountable, then there is no paradox at all. We shouldn't expect to see evidence of galaxy-spanning civilizations because such civilizations cannot exist given the combination of self-destruction risks and resource constraints and evolutionary limitations and cosmic catastrophes and fundamental physical limits. Civilizations emerge occasionally throughout galactic history in scattered locations, but go extinct within thousands to millions of years before achieving galactic visibility. The galaxy has hosted many civilizations over billions of years, but never hosts more than a handful simultaneously. This resolution requires no appeal to speculative scenarios like zoo hypotheses or simulations, but follows from straightforward analysis of the barriers facing civilizations. The barriers are individually well established, including nuclear war risk, pandemic risk, environmental degradation, supernova sterilization, resource depletion, thermodynamic limits. Each barrier is based on known physics and observed phenomena, not speculation. Combining these barriers shows why progression to advanced status is extraordinarily unlikely without requiring any single barrier to be absolutely insurmountable. The resolution explains several observations beyond just the absence of detected aliens. It explains why SETI has found no signals despite decades of searching. If civilizations typically exist for only thousands to millions of years and are separated by thousands of light years, the probability that a civilization is broadcasting when we're listening is very low. Furthermore, civilizations might not broadcast much because they recognize the futility given the distances and time scales. They might use point-to-point communications, or might use technologies we're not monitoring for, or might simply not communicate much once they realize they're alone. The resolution explains why we see no megastructures like Dyson spheres in astronomical surveys. If civilizations don't progress to the level of large-scale stellar engineering before going extinct, then Dyson spheres never get built. Furthermore, as I discussed, resource constraints and diminishing returns might make such megastructures impractical even for civilizations that survive longer than most. The energy and material requirements for a Dyson sphere exceed what might be available or worthwhile. Natural selection at the civilizational level favors efficiency, not megaprojects. The resolution explains why Earth hasn't been visited by aliens. If the nearest contemporary civilization is thousands of light years away, and civilizations typically exist for less than 1 million years, the probability that an alien civilization exists close enough to visit and during a time when Earth is interesting is vanishingly small. Earth has been inhabited by intelligent humans for only 300,000 years and has had technological civilization detectable from space for less than 200 years. The window during which Earth is interesting to visiting aliens is a tiny fraction of cosmic history. And if the nearest aliens are thousands of light years away, they won't see our radio emissions for thousands of years. The absence of alien artifacts in the solar system is similarly explained. If no alien civilizations have existed close enough to send probes to our solar system during the 4.5 billion year history of the solar system, then we shouldn't expect to find artifacts. The von Neumann probe scenario, where self-replicating probes spread exponentially through the galaxy, is prevented by the same barriers that prevent biological expansion. Probes face reliability challenges over million-year journeys and resource constraints and lack of purpose if no civilization remains to receive data. Some researchers have proposed that alien artifacts might exist on Earth or the Moon, but remain undiscovered. This seems unlikely given the extent of geological and archaeological exploration of Earth. Ancient alien artifacts will be detectable through their material composition and manufacturing techniques and design features that don't match natural geological processes. No such artifacts have been found despite extensive searching. The Moon's surface has been surveyed and sampled and similarly shows no alien artifacts. The absence of artifacts is consistent with no aliens visiting during solar system history. So, the resolution to the Fermi Paradox provided by the impossibility of advanced civilizations is that civilizations are rare in space and time, and short-lived, and confined to small volumes, making detection extraordinarily unlikely. We don't see aliens not because they're hiding or because we're alone in the universe, but because civilizations exist in isolated pockets of space and time and go extinct before achieving visibility. This is the hard filter explanation, where the filter is not any single barrier, but the combination of many barriers that together make advanced civilization nearly impossible. This resolution is satisfying because it requires no speculative physics or improbable sociology, but follows from extrapolating known threats and limitations. It's consistent with what we observe, including absence of signals and megastructures and visits. It explains why the galaxy appears empty despite billions of years for colonization. It removes the need to invoke anthropic reasoning or simulation hypotheses or other exotic explanations. The universe is exactly as we would expect if intelligence is common, but advancement is nearly impossible. Now, let me examine what the non-existence of advanced aliens tells us about the nature of intelligence and technology and whether there are fundamental limits to how advanced civilizations can become. The science fiction imagination often depicts civilizations advancing without limit over millions or billions of years, becoming godlike entities with near-magical powers over matter and energy and space-time. These scenarios include Kardashev-type III civilizations controlling entire galaxies, transcendent civilizations uploading consciousness to computers or energy fields, post-biological civilizations expanding at light speed through the universe, civilizations manipulating space-time or creating pocket universes. But the analysis I've presented suggests there are ceilings on advancement beyond which civilizations cannot progress regardless of time available. The fundamental physical limits on energy use and information processing and travel speed impose constraints that no technology can overcome. Thermodynamic limits require that energy use produces entropy and degrades useful energy into waste heat. Computational limits from the Landauer principle and Bremerman's limit cap information processing regardless of computer architecture. The light speed limit prevents faster-than-light travel and communication, limiting how quickly civilizations can expand or even maintain coherence across distances. These limits mean that civilization advancement follows an asymptotic curve, where capabilities increase rapidly initially but approach ceilings as fundamental limits are reached. A young civilization advancing from pre-industrial to industrial to nuclear to space age sees dramatic capability increases over centuries. But further advancement becomes progressively more difficult and expensive with diminishing returns. A civilization might continue advancing slowly for thousands or millions of years, but never achieves godlike powers because physics doesn't allow it. The concept of the Kardashev scale, which classifies civilizations by energy use, illustrates the limits. Type 1 civilizations use all energy available on their planet, roughly 10 to the power of 16 to 10 to the power of 17 watts for Earth. Type 2 use all energy from their star, roughly 10 to the power of 26 watts for the Sun. Type 3 use all energy from their galaxy, roughly 10 to the power of 37 watts for the Milky Way. The progression assumes civilizations steadily increase energy use over time, eventually reaching galactic scales. But as I've discussed, the barriers to interstellar expansion make Type 3 civilization likely impossible. Even Type 2 faces severe challenges in building structures to capture all stellar output. Furthermore, increasing energy use doesn't automatically translate to increasing capabilities in meaningful ways. A Type 2 civilization capturing all solar output has 10 billion times more energy than current human civilization. But what would they do with it? The civilization still faces constraints from intelligence being computationally limited and travel being light-speed limited and resources being finite. Having more energy doesn't overcome these fundamental constraints. It allows doing more things faster or at larger scale, but doesn't enable qualitatively different capabilities. The hypothesis that advanced civilizations might transcend physical limitations by uploading consciousness or becoming energy beings is speculative and probably incoherent. Consciousness appears to be a process implemented by physical substrates, whether biological brains or potentially computers. Calling something that exists as a software pattern transcendent or an energy being doesn't change the fact that it requires a physical substrate to run on and obeys physical laws. Uploaded consciousness faces the same limitations as any computational system, including energy requirements and thermodynamic limits and hardware reliability. It's not transcendent, but just a different implementation of intelligence. The idea that sufficiently advanced technology becomes indistinguishable from magic, as Arthur C. Clarke suggested, is misleading. Advanced technology might appear magical to primitive observers who don't understand the principles, but it's not actually magical and must still obey physical laws. There's no level of advancement where physics stops applying. A civilization might develop technologies we can't currently imagine, but these technologies will still be constrained by conservation laws and thermodynamic laws and relativity and quantum mechanics. They won't be able to violate these laws through clever engineering. The limits on advancement suggest that civilizations might reach a plateau where further progress is impossible or not worthwhile. At this plateau, the civilization has approached fundamental limits in key areas like energy efficiency and computational power and material strength, and has achieved a comfortable existence meeting its needs. Further research produces diminishing returns with enormous investment required for small advances. The civilization might rationally decide to maintain its plateau level rather than investing resources in marginal improvements. This steady-state condition could persist for extended periods. But plateau civilizations still face extinction risks from cosmic catastrophes and internal problems. Maintenance of complex technological systems requires a sustained effort and expertise and resources. If any of these fail, the civilization might decline rather than maintaining the plateau. Furthermore, plateau civilizations are vulnerable to supernova sterilization and other external threats they cannot control. Long-term survival remains uncertain. Even for civilizations that achieve steady state, the eventual fate is likely extinction, not indefinite persistence. Some philosophers have argued that there might be something like an intelligence limit beyond, which further increases in cognitive capability, provide no benefit, or are impossible to implement. If intelligence is fundamentally about pattern recognition and prediction and planning, there might be diminishing returns to increasing intelligence beyond some point. A sufficiently intelligent being can already solve most problems optimally, and further intelligence provides little advantage. Biological constraints like brain size and energy cost might set soft limits. While artificial intelligence doesn't face these specific constraints, it faces other limits from computational costs and training data requirements. The absence of superintelligent AI in the universe despite billions of years available for development might indicate that such AI is either impossible to create or self-destructs, or doesn't provide the advantages often imagined. The scenario where AI rapidly becomes superintelligent through recursive self-improvement assumes that intelligence improvements have increasing returns, where smarter systems can make themselves even smarter faster. But this might not be true if intelligence improvements have diminishing returns, where each increment of intelligence is harder to achieve than the last. Recursive self-improvement might stall at some level rather than exploding to infinity. So, examining limits on advancement reveals that civilizations probably cannot become arbitrarily advanced, but face ceilings imposed by fundamental physics and diminishing returns and resource constraints. The science fiction concept of godlike civilizations is probably fantasy, not a reachable future. Civilizations advance significantly from primitive origins, but plateau at some intermediate level determined by physical limits and practical constraints. They persist at this plateau for an uncertain duration before eventual extinction. The progression from intelligence to advanced civilization is not an unlimited trajectory, but bounded process with definite endpoints. Now, in this final extended section, let me reflect on what the extinction of all advanced aliens means for existential meaning and how we should think about humanity's place in the cosmos given this reality. The traditional religious worldview that humanity is central to a divine plan and has special significance in the cosmos has been progressively undermined by scientific discoveries showing that Earth is not the center of the universe, and humans are products of natural evolution, not special creation. And the universe is vast and ancient, with humans occupying a tiny, insignificant fraction of space and time. The principle of mediocrity, or Copernican principle, suggests we shouldn't assume we're special, but should expect to be typical. But the analysis showing that advanced aliens don't exist and that most intelligent species go extinct suggests that humans might actually be special in certain senses, not through divine intervention, but through contingent luck surviving barriers that eliminate most species. We're not special in being deliberately created, but we're special in being rare survivors of multiple filters. The universe is mostly empty of intelligence, not because intelligence is impossible, but because it's difficult to achieve and maintain. This makes conscious beings like humans rare and precious from a naturalistic perspective, without requiring a supernatural explanation. The question of cosmic meaning takes on a different character in a universe where consciousness is rare and temporary. Traditional sources of meaning include fulfilling divine purpose, or participating in cosmic progress toward greater complexity and consciousness, or joining a galactic community of minds. But if there's no divine purpose and no cosmic progress and no galactic community, where does meaning come from? The existentialist's answer is that meaning is created by conscious beings through their choices and values and commitments. It's not found in the universe, but generated by subjects experiencing the universe. This subjective origin of meaning might seem to diminish it, making meaning merely arbitrary human construction without cosmic grounding. But this conclusion doesn't follow. The fact that meaning originates in consciousness doesn't make it less real or important to conscious beings. Love and friendship and beauty and truth are valuable to those experiencing them, regardless of whether the universe cares. The mistake is thinking that value requires cosmic endorsement, when actually consciousness is the source of all value and needs no external validation. Furthermore, the rarity of consciousness in the universe might actually enhance meaning rather than diminish it. If consciousness is a common cosmic phenomenon, then individual conscious beings are replaceable and insignificant. But if consciousness is rare, then each conscious being is a precious, unique phenomenon that represents something extraordinarily unlikely and temporary. The value of conscious experience is increased by its rarity, not decreased. Diamonds are valuable partly because they're rare, while abundant rocks are not. Similarly, rare consciousness is more precious than it would be if consciousness were common. The temporariness of consciousness and civilization also doesn't eliminate meaning, but contextualizes it within a finite scope. Our lives and our civilization will end and will be forgotten, and the universe will continue indifferently. But this doesn't make our experiences and relationships and accomplishments meaningless during the time they occur. A beautiful sunset is valuable in the moment of experiencing it, even though the sunset passes and is forgotten. The meaning is in the experiencing, not in the permanence. Accepting impermanence allows focusing on making experiences valuable rather than lamenting their transience. The responsibility for creating meaning falls entirely on conscious beings. Since there's no external source providing meaning, we must decide what values to pursue and what kind of civilization to build and how to use our brief time. This is simultaneously liberating and daunting. Liberating because we're not constrained by cosmic purpose and can define our own values. Daunting because we bear full responsibility for our choices with no authority to appeal to. The existential burden of freedom requires that we choose wisely about what matters and act according to our choices. The possibility that human extinction would eliminate possibly the only or one of very few consciousness-bearing civilizations in our galactic region creates an ethical imperative to preserve humanity and the conditions for future consciousness. This is not because humans have intrinsic cosmic significance, but because consciousness has value and eliminating consciousness eliminates value. The ethics of consciousness preservation is grounded in the valuing of consciousness, not in metaphysical claims about human importance. Allowing preventable extinction is wrong because it eliminates something valuable, not because it violates a cosmic plan. Some have argued for long-termism, which prioritizes the interests of future generations and long-term consequences over short-term benefits. If humanity persists for millions of years, the total well-being of future generations might vastly exceed current well-being, making actions that increase long-term survival probability extremely valuable, even if they have cost today. The argument is that we should make substantial sacrifices now to reduce existential risks and improve long-term prospects because the stakes are so high. A small reduction in extinction probability multiplied by the enormous potential future population creates huge expected value. Critics of strong long-termism argue that it's unclear we can meaningfully affect long-term outcomes given uncertainty, and that prioritizing the distant future over the present might justify ignoring current suffering. Furthermore, if, as I've argued, civilizational lifespans are likely limited to millions of years by unavoidable barriers, then the total potential future population is smaller than some long-termists assume. But even millions of years of civilization containing trillions of individuals is enormous compared to the current population, suggesting some long-termist concerns remain valid. The practical question is how to balance reducing existential risks with addressing current problems. Existential risk reduction is important, but shouldn't be pursued at the expense of all other values. We should care about current well-being and reducing current suffering, even while also caring about long-term survival. Finding an appropriate balance requires wisdom and careful analysis of trade-offs. Fortunately, many interventions help both current well-being and long-term survival, like pandemic prevention, which reduces current disease burden and reduces extinction risk, or climate mitigation, which helps current populations and preserves habitability. The cosmic perspective that we're alone or nearly alone and facing these challenges without guidance or help from advanced aliens is sobering, but also empowering. We cannot look to superior beings for solutions or rescue, but must solve our problems ourselves using our intelligence and cooperation. The responsibility is entirely ours, which is daunting, but also means our choices matter, and our success or failure in navigating existential risks determines whether consciousness persists in our region of the galaxy or goes extinct. The stakes are high and the outcome is uncertain, but we have agency to affect the outcome. The cultural and philosophical implications include rethinking the human relationship with nature and technology. If technology creates existential threats that increase with advancement, and if unlimited technological progress leads to extinction, not to transcendence, then perhaps we should be more cautious about technological development and should carefully assess risks before deploying powerful technologies. The precautionary principle suggests we should err on the side of caution when facing potentially catastrophic risks, even if probabilities are uncertain. Applying this principle to technologies like nuclear weapons and engineered pathogens and advanced AI seems prudent. But technology also provides solutions to problems, including some existential risks. Asteroid detection and deflection requires technology. Pandemic response requires biotechnology and medical technology. Climate change mitigation might require advanced energy technologies and geoengineering. We cannot simply reject technology without losing capabilities we need for survival. The challenge is developing beneficial technologies while controlling dangerous ones. This requires wisdom and institutions capable of long-term thinking and international cooperation, none of which are guaranteed, but all of which are possible if we choose to pursue them. The educational implications include teaching a realistic understanding of humanity's situation, including our cosmic insignificance and rarity and the existential risks we face. Current education focuses on cultural narratives of progress and human specialness, or alternatively on environmental narratives of human destructiveness. A more balanced and accurate education would teach that humans are products of natural evolution in an indifferent universe, that consciousness is rare and precious, that we face serious risks of extinction from both natural and self-inflicted causes, that our choices matter for determining whether humanity persists, and that meaning comes from consciousness, not from cosmos. Such education might be psychologically challenging, particularly for younger people who might find cosmic insignificance depressing. But hiding reality serves no purpose and might be counterproductive if it leads to complacency about existential risks. Better to understand reality honestly and find meaning within that reality rather than constructing comforting myths that don't withstand scrutiny. Furthermore, understanding our cosmic context might inspire greater appreciation for life and consciousness and motivation to preserve them, given their rarity and preciousness. The implications for how we conduct space exploration and SETI include adjusting expectations to recognize we probably won't find advanced aliens, but might find evidence of microbial life or of extinct civilizations. Exploring exoplanets for biosignatures is valuable for understanding how common life is and whether Earth is unique biologically. Searching for technosignatures from current civilizations has low expected success, but might be worth some effort given the enormous implications if successful. Exploring the solar system for extinct alien artifacts or for evidence of past alien visits might be worthwhile, despite low probability. In conclusion, advanced aliens don't exist, not because intelligent life never evolves, but because the barriers to achieving advanced status are nearly insurmountable given the combination of self-destruction risks from nuclear war, engineered pandemics, AI, and environmental collapse, resource depletion and diminishing returns on technological progress, evolutionary and cognitive limitations preventing indefinite advancement, cosmic catastrophes, including supernovae and asteroid impacts, fundamental physical limits on energy and information and travel, social and political instabilities, loss of motivation or drive, and the sheer millions of years required during which any threat can cause extinction. They all went extinct because multiple barriers, each with moderate extinction probability, compound multiplicatively to create an overall survival probability approaching zero. Most intelligent species die during technological adolescence from self-destruction. The few that survive this phase face resource constraints and cosmic catastrophes over millions of years, eventually causing extinction. Virtually no species successfully navigates all barriers to achieve truly advanced, galactic-scale civilization. At any given time, perhaps 0 to a few dozen civilizations exist across the entire galaxy, separated by thousands of light years, making detection impossible. Over galactic history, thousands to millions of civilizations have emerged and gone extinct, leaving no trace. The implications are that the Fermi Paradox is resolved by recognizing advanced civilizations cannot exist given multiple barriers. Humanity is among the rare survivors of filters that eliminate most species, making us precious, if not unique, in our galactic region. We face serious extinction risks over the next thousands to millions of years that could end our existence if we're not careful. Existential risk reduction should be the highest priority to maximize our probability of long-term survival. Meaning and value come from consciousness, not from cosmos, making consciousness preservation ethically imperative. We should maintain realistic expectations about technological limits while pursuing sustainable civilization on Earth over millions of years. Accepting cosmic insignificance is liberating rather than depressing when it allows focus on creating valuable, conscious experiences during our temporary existence. They all went extinct, but we haven't yet, giving us both responsibility and opportunity to persist as long as possible. Thank you.